Howdy, Pre-Cal. It is Miss Kosh. We are going to do all things sequences and series all in one worksheet, one set of notes. I'm calling this the quick teach because we have just had kind of a chaotic schedule. So, ready or not, here we go. Here is our formula chart at the top. And first of all, it's an arithmetic. It looks like arithmetic, but it's arithmetic. An arithmetic sequence has a common difference. Okay, and then its formulas are given here. We will use them as we go. And then these are the partial sum. These are the finite sums. And it doesn't have an infinite sum. So as soon as you see arithmetic and they try and have you make it sum to infinity, you have to say it does not exist, okay? Then the other type that we're studying are geometric sequences and series, and they have a common ratio. Okay, and so here are their formulas. We're going to use them as we go. Here is the summation. So this is a finite sum, and here is the infinite sum, but we're going to discover in a little bit that not every infinite geometric series will have a sum. So some will diverge and some will converge, and we'll talk about that too. Okay, so here we go. We've got this sequence. It's going 24, 31, 38, 45. Hopefully you recognize that we are adding the same thing. This sequence is arithmetic because it has a common difference. And that common difference, what we were doing is we were adding 7 each time. No, we were not adding 7. What were we doing? We were subtracting 7. So our D value, our common difference, is -7. Okay, so the first way to write our formula is a recursive formula. And with that, you have to tell me where to start and what to do. Okay, so always where to start and what to do. On this one, so the first term was 20. No, I'm sorry, it's been a week. We are adding 7. This is a positive 7. Did you catch my mistake before? Good job. Good for you. I caught it eventually. So our common difference is D equals 7. We are adding 7 each time. I don't know where I was going with that. Okay, so we started at 24. That's our first term. And now if you think about it, this would be A sub 1. This would be A sub 2. Here's A sub 3. Here's A sub 4. Somewhere out here in this list is A sub n. And the term that comes right before it, is A sub n minus 1. The term that comes right after it is A sub n plus 1. Okay, and so to find the nth term, recursively, we go to the term right before it, A sub n minus 1, and then we add 7. Okay, in our explicit formula, we're going to use one of these up here. So A sub n equals A sub 1 plus n minus 1 times D. And we're going to plug in what we know. So the explicit formula is where we want to come up with a rule for A sub n. The first term was 24 plus n minus 1. Our common difference is 7. We can clean this up a little bit, and oh, that was funny. What did I do? Not sure how I did that. My apologies. And we have 7n. I see a minus 7, so 24 minus 7 is 17. And this is our explicit formula. Okay, now it says find the 12th term of the sequence. So what I need to do A sub 12, and I'm going to plug in a 12. Okay, let's see, is Desmos, come here, Desmos. There you are. Let's see if I can split my screen nicely. There we go. And so we have a 7 times 12 plus 17, and we see that the 12th term, A sub 12, will be equal to 101. So this is the 12th term. That's kind of this is our input value. It's like our x, but not, and this is the value of the term, and it would be our output value. Okay. Now the next one, find n. Okay, so on this one, they're telling you we've got a term whose value is 192. What term is that in our sequence? So what we're going to do is we're going to look at the formula right above. It's written there for us, and we're going to plug in 192 for A sub n. And then, okay, come back, Desmos. We're going to take 192 and subtract 17, get that answer. And then take 175 and divide it by 7. Okay, and so we end up with, what was that? 175 equals 7n, divide by 7, we get n equals 25. And so the 25th term of this sequence has a value of 192. Now, we are looking at this same, so now what we have is I took these same numbers and I copied and pasted, but then I no longer have commas between them, I now have plus signs. This is now a series, and this is a finite. You could tell me this is a finite series, or you could tell me this is an arithmetic series. Kind of either word goes in that blank, and I kind of wanted you to be aware of both of them. It's a finite series because I stopped somewhere. I had a final term of this series. I said, okay, we're gonna add these different terms. I have a dot, dot, dot. This is a finite series because it is the sum of the terms of a sequence. So a sequence has separated, the terms are separated with commas. A series, you have plus signs or minus signs if things are negative. Okay, so find n when a sub n equals, so we had, remember it was 7n, so 129 is equal to 7n plus 17, so we're going to subtract 17. That gives me 112 is equal to 7n. Let's see if I can divide, that's 1, no, did I do something wrong? 42 would be, excuse me, it would be 6. Okay, and so this term right here is the 16th term of our series. So we can take this series and we can squish it together and write it in a nice small way using what we call sigma or summation notation. I feel like I just quoted the cartoon that I'm going to make you watch. That's almost verbatim how they say it. And so what it is, it's the sum. We do this capital Greek letter, capital Greek letter. Anyway, it's a capital letter. It's Greek. That means that's sigma. And we're going to say as n goes from 1 to 16. So we were adding up 16 terms here. And we take our rule, the explicit formula, and we're going to put this in here. And that would be the sigma or the summation notation for this particular problem. Okay, find the sum. So now, since this is arithmetic, we have to use one of these two formulas. So if we know the first term and we know the last term that we want, we can use this version. This other one right here it doesn't require you to know the last term. It asks you to know the common difference, which we do. I'll work it the first way and we'll see what we think. Okay, so this is the sum of 16 terms, so S sub 16. And our formula was n over 2 times a sub 1, the first term we care about, which was 24, plus the last term we care about, which is 129. Okay, come back, Desmos. Okay, so 24 plus, that's not a plus, 24 plus 129 is equal to 153. So now I need to do 8 times 153. Did you see where I got that? 8. So 153 times 8 is equal to 1,224. So the sum, if I were to write out all these numbers in this series and then add them all up, it would equal 1224. It says, if this were an infinite series, if we had said this instead, the sum as n goes from 1 to infinity of 7n plus 17, would it converge or diverge? So basically what's happening, we keep adding bigger and bigger and bigger and bigger numbers. When you think, oh, I have found the biggest that this sum could be, I'm going to go second, and I'm going to add the next term, and my number is bigger. So as soon as you think, oh, this is as big as it's ever going to get, I'm like, nope, I go next. I add the next term of my series, and it's bigger. And so this one will diverge, and we would say here that the sum does not exist. Okay, so all arithmetic series diverge. Converge means you can find a particular value, and this is really helpful. Watch that cartoon where they're walking to the wall. That is something that would converge, whereas as the numbers get bigger and bigger and bigger, they diverge. Okay, now we're on to our next one. We've got 2 more that we're going to look at. Okay, the sequence is, okay, so let's see what's happening. I'm adding, 96, and then I'm adding, not 96. Okay, so let's use Desmos and see what's happening here. I'm thinking that if I took the second term and divided it by the first term, let's make that a fraction. And then if I took the third term and divided it by the second term and make that a fraction, do you see how I'm making things? Fractions are great in series and sequences. Divide that by that term. Okay, notice they all have what we call a common ratio, and that common ratio, did my pen turn off? It did. Where r is equal to 5/2. Okay, this sequence is geometric because it has a common ratio where r equals 5/2. So our recursive formula, once again, you have to tell me where to start and what to do. A sub 1 equals 64. That's where we start. And now to find the nth term, we have to go to the previous term, a sub n minus 1. And I like to say I'm not grading your handwriting, but I'm grading your handwriting. That really needs to be a subscript. So if I see something like a sub n minus 1, nope, no good. If I see a sub n minus 1, no good. If I see, so don't do anything like that. We got to be careful about our handwriting. We need this to be in the subscript, all of it down there together. Okay, so be careful with that. If you have sloppy handwriting, work on it, because I'll be mean and nasty and take off points. No, we can leave that there. Okay, so on this one, what were we doing? So we went to the term right before it, and we multiplied it by the common ratio of 5/2. And so that's the recursive formula. The explicit formula shows up in our chart right here. We can go to the first term and multiply it by r to the n minus 1. So this becomes a sub n is equal to the first term times r to the n minus 1. Okay, so now find the sixth term of the sequence. And so I want a sub 6 is equal to 64 times 5/2 to the 6 minus 1. I just plugged in 6 for n. Well, now, I would caution you about going straight to Desmos and just plugging this in because a lot of these geometric sequences and series work better with fractions. So what I see is 64. I know my powers of 2. 2 times 2 to the first is 2, to the second is 4, 8, 16, 32, 64. So what I'm saying here is that 2 raised to the 6th power is 64. So this is 2 to the 6th. Times, this will become 5 to the 5th, 6 minus 1 is 5, over 2 to the 5th. And so then the 2 to the 6th divided by 2 to the 5th ends up just giving me, this is 2 times 5 to the 5th. This one isn't a fraction, but it could have been. And so working like this will help deal with those fractions. So I need to do 2 times 5 raised to the 5th power, and I get that my sixth term, a sub 6, is equal to 6,250. All right. Okay. Oh, this is gross. So here's my point with fractions. So they said find a sub n. They want to know what term is this in my sequence. Well, that's kind of hard to tell. So I have 9, 7, 6, 5. I am not nice. Why did I write this problem? I mean, I did this myself. Okay. Is equal to 64 times 5/2 to the n minus 1. Okay, we need to get rid of the 64, so we're going to multiply both sides by 1/64. Okay, and then let's see. What I'm hopeful for, okay, so here's what I see without even actually going to my calculator. 64, we just had 2, 4, 8, 16, 32, 64. This is 9, 7, 6, 5, 6, 2, 5 over 2 to the 6th times 16 is 2, 4, 8, 16. This is 2 to the 4th, okay, is equal to 5. So here's what I see. We're going to work smarter, not harder. Yes. Okay, I see a 2 to the 10th in the denominator. So it would be really, really helpful if 5 to the 10th were in the numerator. Let's see if we could be so lucky. Why did I want 5 to the 10th to be in the numerator? Because I'm trying to get the same base on this side as I am on the other side. And so I see this 5/2, so I'm hopeful that this is a power of 5 and this is a power of 2. Okay, that's the hope. So let's see. We just said 5 raised to the 10th power. Oh, look at that. This is lovely. So we have 5 to the 10th over 2 to the 10th, which we could write as 5/2 all raised to the 10th, which is equal to 5/2 to the n minus 1. And so now 10 is equal, since our bases are the same, we can set the exponents equal. 10 is equal to n minus 1, so n would be equal to 11. A little bit of a beating, but we made it. Okay, so now I'm taking this same set of numbers and I am turning it in from, oh, I have a typo. Okay, I will try and fix that before I give you access to the PDF. These should all have plus signs, my bad. Well, I got it now. Okay, so this is a finite. Actually, I want it to be in blue. A finite series, or you could say it's a geometric series, because it is the sum of the terms of a sequence. I will try and remember to fix that. Okay, so find a sub n. We're trying to figure out, here's the first term, the second term, the third term, the fourth term, and some random term, we don't know what it is. But when we go to write the sigma notation, we're going to go from the first term to whatever term that is. We wrote our rule. Where did it go? Over here, 64 times 5 halves to the n minus 1 goes in our summation notation. Notice back here, anything with addition, you have to put in parentheses. And if it doesn't have addition, if they're multiplying, you can put this in parentheses, but you don't have to. Okay, it's a good habit. But we don't know what our top number is yet, so we've got to figure that out. And that's what we're going to do right here. So I have this 78125 over 2 is equal to, it was 64 times 5 halves to the n minus 1. I'm going to multiply both sides by 1 over 64 to get rid of that 64. We have said 64 was 2 to the 6th, so this becomes 78125 over 2 to the 7th power, because here's 2 to the 6th, and then we have one more right here. 6 plus 1 is 7. And so we're hopeful. Let's see. Let's hope, fingers crossed, that 5 to the 7th power is that number that we're looking at in the numerator. Where did it go? Right here. Okay, we want 5 raised to the 7th power. Hallelujah. Okay, so this is 5 over 2 raised to the 7th power, which is equal to, we've gotten rid of the 64, so it's equal to 5 over 2 to the n minus 1. So if 7 equals n minus 1, I can say n is equal to 8. Okay, so it's the sum as n goes from 1 to 8. This right here was the 8th term we just discovered. And, okay, find the sum of the series above. So now this is a geometric series. Let's go back to our table. And our partial sum looks something like this. It's the sum of n terms is equal to a sub 1 times 1 minus r to the n over 1 minus r. So it's the sum of 8 terms is equal to our first term times 1 minus our r value, is 5 over 2 to the 8th power, because we're raising it to the 8th over 1. I didn't say it correctly, but I wrote it right. Okay, and now we do want Desmos. It's going to be very helpful. And it might be, well, sometimes, okay, let's type this in. 64 times, and then I'm going to need to make this a fraction. So I can do this and have 1 minus. Let's practice putting this in parentheses, and I know that seems silly. It doesn't matter when it's positive. It sure does matter when it's negative. So we'll practice doing it all the time just so we don't make a mistake. 5 over 2. This one, well, same idea. Let's practice with parentheses here. It didn't change anything, but there we go. Let's see, does it give us a fraction? Okay, this would be exactly equal to, the pen turned off again, what do you know? It would be exactly equal to 130,123 over 2, which actually is equal to 65,061.5. All right, there we go. Okay, so now on this one, notice my numbers keep getting bigger and bigger and bigger and bigger and bigger. So if you're going to add, so we found the sum of the first 8 terms. If I found the sum of the first 10 terms, it would be even bigger. If I found the sum of the first 12 terms, it would be even bigger than that. And it would keep getting bigger and bigger and bigger and bigger. So this series will diverge. Some geometric series converge, but their R value, our R value was 5 over 2. Well, this is bigger than 1, and that means that's no good. In order for it to converge, the R value has to be small. It has to be between 0 and, well, that's not true. The absolute value of R has to be less than 1, okay? And this is not that case, so we will not converge, we will diverge. Okay, we've got one more example that we're going to look at. And here we go. Oh, check this out. This sequence is going negative, positive, and so forth. Did I forget to put the plus signs? Nope, I remembered here. Okay, well, I'm good, but I'm not perfect. Okay, so let's look at this one. What we had done before, do you remember? We came along and said, let's take the second term, 54, and divide it by the first term. Okay, let's make that a fraction. Okay, let's take the third term, negative 36, and divide it by the second term. Ah, that's the same value. That's a good sign. This is 24 divided by that negative 36. Make that a fraction, and there we go. Okay, so this is a geometric series. You know, when you have it on the eraser, it doesn't write. Funny. This is a geometric series. This sequence is geometric because it has a common ratio where r equals negative 2/3. So the recursive formula tell me where to start and what to do. A sub 1 is equal to negative 81. A sub n equals negative 2/3 times the term that came right before, a sub n minus 1. The explicit formula a sub n is equal to a sub 1 times r to the n minus 1. And now here, parentheses matter like crazy. You got to have the parentheses because when you raise a negative to an odd power, it stays negative. When you raise a negative to an even power, it becomes positive. Okay, so find the eighth term of the sequence. A sub 8 is equal to negative 81 times negative 2/3 to the 8 minus 1. Where is Desmos? Here we go. Okay. Sometimes it's helpful to turn this into, to make this a fraction. 81 times, what did we say here? Parentheses. Got to have your parentheses, especially when it's negative. Then come out and do those parentheses. Raise that to 8 minus 1 is 7. Will it give me the fraction? It does give me the fraction, and the fraction's a little bit easier to work with. And it's positive because we ended up with a negative times a negative ultimately. And so the value of the eighth term is 128 over 27, which is approximately equal to 4.74, well, 1. There we go. But I prefer this. I like that number better. Okay, now let's see what to find in. Now they've given us a value. Okay, so already this 32 over 3 is going to be smaller, or it looks like it, actually it's bigger than 128 over 27, but here's what I see. We're multiplying by something over 3, and so it's going to be, if it should happen before we get to the eighth term. Let's see if we're right. Okay, so 32 over 3 is equal to negative 81 times negative 2/3 to the n minus 1. I'm going to multiply both sides by a negative 1 over 81, or I could have said 1 over negative 81. And so 81 is, powers of 3, 3, 9, 27, 81. This is 3 to the third, to the fourth times another 3 to the fifth. So I see a 32. I want to go back to blue. I see a 32 over a negative 3 to the fifth power is equal to a negative 2/3 to the n minus 1. Now I'm hopeful that that 32 is 2 to the fifth. Let's see. Well, come here, Desmos. What are you doing? Okay, so let's see. If I have 2 and I raise it to the fifth, it's 32. Oh, hallelujah. Okay, so this becomes a negative 2 over 3 to the fifth power is equal to a negative 2 over 3 to the n minus 1. The bases are the same. We can set the exponents equal. 5 equals n minus 1, add 1. We get that is the sixth term of our sequence. Okay, now, what do you notice? Look at this. We have a denominator of 3, a denominator here of 27 here, 3 here, and now on this one, we're going to have a denominator of 9. I bet it comes between the two of them, but let's see. Okay, this is a finite, well, and it's a geometric series because it is the sum of the terms of a sequence. So we need to find that in when we have a negative 64 over 9. Okay, so negative 64 over 9 is equal to negative 81 times negative 2/3 to the n minus 1. Let's multiply both sides by, let's use our calculator. Let's see, if I have 9 times 81, Okay, so this, I'm hopeful, let's see, 2 to the 6th, does that give me 64? And 3 to the 6th, oops, sorry, that's not what I meant. Okay, and 3 to the 6th. Okay, so this is about to become a negative 2 over 3, all raised to the 6th power, is equal to a negative 2 over 3 to the n minus 1. So I can set the exponents equal. 6 equals n minus 1, add 1. This is the 7th term of my series. Okay, so write the series in sigma notation. This is the sum as n goes from 1 to 7 of, what was my rule? Negative 81 times negative 2/3 to the n minus 1. Find the sum. Okay, so let's use that formula that we just saw. It's the sum of 7 terms, which is equal to the value of the first term, negative 81, over 1 minus, our R value is negative 2/3 to the 7 over, there we go, let's make it so you can see what I'm doing, over 1 minus negative, and that is what we need to plug into Desmos. Negative 81 times, let's make that fraction, 1 minus, and now, oh, did I do that right? Did I hit that? 1 minus, there we go. Let's use parentheses. We need a negative 2/3. Come out of that, close that parentheses, raise that to the 7th power, and that needs to be over 1 minus, in parentheses, a negative 2 over 3. Close that parentheses, close, oh, no, we don't need a parentheses there. We kind of need a parentheses here, but it's not going to change anything. Okay, there's that fraction. So the sum is equal to negative 463 over 9, which is approximately equal to negative 51.444. Okay, and so now it says, if this were an infinite series, would it converge or diverge? It would converge. Okay, our R value was equal to negative 2/3. The absolute value of negative 2/3 is 2/3, which is less than 1. And so that will converge. So now we use the formula. It is right here. Sometimes, maybe I should be in the habit of writing that infinity. Sometimes I just get lazy and don't. If I just have an S for sum and there is no indication here, it's the same thing as saying it's the infinite sum. Okay, and so it's a sub 1 over 1 minus r. Where did we go? Here we are. Equals a sub 1 was a negative 81 over 1 minus our r was a negative 2/3. Desmos, we need you. Okay, negative 81 over 1 minus, in parentheses, a negative 2/3. And let's see, what's that fraction? This would be equal to a negative 243 over 5, which is about, it's exactly negative 48.6. Okay, there's a couple more things that I need to make sure we understand, but I'm going to have to do that in a different video and on a different worksheet. I think this was a very good summary of all things sequence and series, and I have this exact setup, but with new numbers. So do that for homework. Like, subscribe, comment, and go practice. Good luck to you.